Okay, this webcast is going to continue looking at Newton's second law, but now we're going to look at situations where there are forces in multiple directions, not just parallel to a single axis, and we may have some component forces. Let's look at number 12, where we have a roller coaster going down a hill, and we're going to assume that friction is small enough that we can ignore it. Since the roller coaster is moving in this direction down the hill, I'm going to tilt the coordinate axes so that one axis here is parallel. I'll call this my x-axis, is parallel to that direction of motion. And then I'm going to make another axis that's perpendicular to that. That's the y-axis. Okay. So this roller coaster has a weight, and that's the gravitational force by the Earth. And let's see, it's 300 kilogram car. So 300 times 9.8. So that force of gravity is 2940 newtons. And the hill, or the track, is supporting the roller coaster, so there's a normal force perpendicular to the track. We're ignoring friction, so I'm not going to show friction. And I think these are the only forces, but I do want to, or I need to draw the components of the force of gravity so that I can show the x component that's parallel to the x-axis and the y component that's parallel to the y-axis. Now, they've told me that this angle right here is the inclination angle of this track is 65 degrees. If that angle is 65, looking down at this triangle here, where this is a right angle, well then this angle up here must be 90 minus 65, which is 25 degrees. Okay, once I have an angle inside the triangle that has the components of the force of gravity, I can find those components. The x component is going to be 2940 times the cosine of 25. Cosine because it's adjacent to that 25 degree angle. And so that is 2,664.5 newtons. And FGY is across the triangle, so we're going to use the sine function. It's going to be 2940 times sine of 25 degrees. And that is 1,242.5 newtons. Okay, so we have all of the forces in this force diagram. It asks us to find the component of the gravitational force parallel to the hill. Well, that's, of course, FGX, and we've already solved for that, 2,664.5 newtons. I'm noticing that in the vertical direction, or perpendicular to the hill, we have the normal force minus the force of the y component of the force of gravity, and that net force in that direction perpendicular to the hill is going to be 0 because it's not moving, up or down in that direction. So therefore I know that the normal force is also going to be 1,242.5 newtons. Okay, but in the direction parallel to the track, there's a net force which is equal to FGX, because that is the only force in that direction parallel to the hill, and therefore the acceleration of the roller coaster is going to be that net force in the direction of motion divided by the mass. And so it's going to be 2,664.5 newtons divided by the 300 kilograms. Which gives us 8.882 meters per second squared as the acceleration of that roller coaster. So it says that at the point that we saw in the figure, the initial velocity is 4 meters per second, and 20 minutes or 20 meters later, so they have a displacement of 20 meters, we've just found their acceleration, which is 8.882 meters per second squared. They're asking us how fast they're going to be going. So, in other words, we're looking at this picture. They start out here near the top of the hill, and they're coming down to near the bottom of the hill 20 meters later. How fast are they going near the bottom of the hill? Well, if we assume a constant acceleration, and I think we can assume that because none of the forces are changing, so that's constant net force, then we can use a kinematic equation. With the things that we know here, the best equation to use would be Vf squared equals Vi squared plus 2 times the acceleration times the displacement. And so the final velocity would be .269 meters per second. Let's do one more example where we have force diagrams where there may be some component forces. Here we've got a worker who's pushing a shipping box along a conveyor belt or a track, and again we're going to ignore friction. Now in this case the box is moving horizontally, so I will not tilt the axes. And so, there's a force of gravity on this box. Which is 68.6 newtons. The man is pushing it in this direction, okay? They're giving us that this angle is 20 degrees, but that means that this angle is also 20 degrees. And I'm finding that angle because I need to find the components of this applied force. So the applied force is 25 newtons. And these two components, here is the x component. It's adjacent to that angle, and so it's going to be 25 times the cosine of 25, or cosine of 20, which is 23.5 newtons. And then the y component here is going to be 25 times the sine of that 20-degree angle, which is 8.6 newtons. Let's see, and then let's not forget that the roller track is supporting the box, and so there's a normal force here on the box by the track, and I don't know what it is quite yet. Okay, so we found the horizontal component of the worker's push. That's Fgx. And that is the only force in the horizontal direction. So in the horizontal direction, the sum of the forces is just Fgx. So it's 23.5 newtons. And so the acceleration is the net force in that direction, because that's the direction the box is moving. So it's going to be the net force in that horizontal direction divided by the mass. So 23.5 newtons divided by the 7 kilograms, which is 3.357 meters per second squared. Okay. And then it said determine the normal force. Well, the normal force is in the vertical direction, so I'd need to take the sum of the forces in the vertical direction. And that's going to be 0, right? The box is not moving in that direction, so all the forces balance in that direction. But if I took the sum of the forces, it would be the normal force minus the y component, the y component of the applied force, and minus the force of gravity. And so therefore the normal force would equal the force of gravity plus the y component of that applied force. And so I could find that out. It's going to be 68.6 plus 8.6. And so it would be 77.2 newtons. In other words, this box was not moving in the vertical direction, so there had to be as much force pulling up on the box as there was pushing down on the box. So again, you know, this type of situation where we have component forces, a little bit harder, more complicated to draw the force diagram, but the basic strategy, again, is to express the net force in two different ways. First, we found the sum of the forces in the direction of motion, and then we used Newton's second law, which says that net force is mass times acceleration.